Hello and welcome back to the ThermoJav channel with another thermodynamic problem solving in the engineering equation solver. In today's video, we are going to determine the saturated liquid vapor mixture properties for a specific problem here. As you can see, we have a rigid vessel with a volume of 90 liters, contains 4.5 kilogram of R134A at a pressure of 180 kilopascal. So today we are going to determine the following properties of this refrigerant: temperature, quality of the saturated liquid vapor mixture, a specific enthalpy, and finally the volume occupied by the vapor phase. At this point, we assume we don't know whether the refrigerant is in the compressed liquid or subcooled liquid, superheated vapor, or saturated mixture region. So this can be determined by comparing a suitable property to the saturated liquid or saturated vapor values, like for example here in this case a specific volume. When look at the given data in this problem, we have the type of refrigerant, the volume of this rigid vessel, total mass, and also the pressure. So with having this volume and the total mass, we can find out the specific volume for this refrigerant at this given data. So we can start first this one with the EES software. So here I will go to this equation windows here, and then I can start to calculate. So from this information given, we can determine the specific volume. So here I can just simply write a comment like the refrigerant name, for example, R134A. So this is actually a comment. So let me go to the option and the preference and increase the size of this font and then press OK to have a better visualization. Then I can start to give the given data. The pressure P1, I will call it at P1, equal to 180. And as you know, here in the actually unit system, if you go here, you can find out the default setting for the units. So here the temperature is Celsius and the pressure unit is kilopascal. So I will keep this default because it is according to our problem. But in your case, if it's a different unit, you can simply change it here in this window. So the pressure is 180. You can also go here and then assign this one, but here it has been assigned to 180 kilopascal. The unit is kilopascal, so I can just skip this part. And then the mass here, the total mass is 4.5 kilogram. So I will call it as the M equal to 4.5. Press enter and we'll go here, and then you see here the unit is in kilogram. So here I simply have this pressure and mass here. And then finally the volume of this rigid vessel is equal to 90 liter, but I can simply multiply by 0.001 to change it to cubic meter. So this volume is in the cubic meter volume. So here for this volume, you have this cubic meter for the unit, and then I will press enter. Then in this part, I'm going to calculate the specific volume. I write a comment here, a specific volume, and then I can call it use one actually Greek letter here for specify the specific volume. Before that, I can go to this formatted equation and see the result. So you cannot see these comments here in this equation window. Then I will go back to the equation and then call this one as Nu refer to the specific volume, which is equal to V divided by M. So you can check the equation. So you have 4 equations and 4 variables, so you can solve simply this equation. And then when you press on the solve, but before that I will go to this formatted equation to see and show this Greek letter here. So as you can see here, simply you can write down the Greek letter. We have another video in this channel. You can find out and see all this Greek unit in that video. Then I can solve this problem, and as you can see, the specific volume for this refrigerant in this given data is roughly 0.02 cubic meter per kilogram. Okay. Now, based on this specific volume, which is 0.02, we can go to a thermodynamic table and also check the VF for fluid and VG for gas status. So we can find out if it is in the compressed. Let me go here and then show to this graph. For example, this is TV graph, and we have some pressure constant. So if we consider this is correspond to 180 kilopascal pressure, if this specific volume is between this VF and VG, these 2 points, so we are working in the saturated liquid vapor region. So we can simply go here and check in this actually thermodynamic table, which is related to actually saturated refrigerant 134A. So for this given pressure 180, this VF and VG is these 2 value 0.0007, and then VG is 0.1 roughly, and the specific volume for our problem is 0.02, which is one value between these 2. So according to this actually graph TV, this specific volume is something between these 2, VF and VG. So we can now we know actually that this refrigerant is in this saturated liquid vapor region. So we can check this point in the ES also. So I will just simply go to the ES, to the equation window, and then start to check. Okay, so I can start and then write a comment at this temperature, given pressure actually 180 kilopascal. I can calculate the specific volume for fluid. Then to do so, I can go to this function information, simply go to the thermophysical properties, find out the refrigerant, which is R134A. Here I can select it under this column, and then I can go to the volume, which is this specific volume. When I click here, you see this unit is cubic meter per kilogram. So I can just first simply paste this equation and modify this one. So first of all, I will change this one to Nu, which represents the specific heat, nu underscore F. So I can simply define this one. And as you can see, this function is volume for this refrigerant, and we need to give 2 data. One is this pressure. So I change this value to P1, or you can just simply write 180, but I will keep it as this P1, which is our input. But here, because we are working in this saturated because now I'm going to find out for the fluid this specific volume here, this point. So in this point, actually the quality of this liquid is 0. and according to the definition of the X or quality. And for this region, which is gas region, so vapor region, it is actually the X is equal to 1. So for this specific volume for the fluid here, I can just simply, instead of temperature, I can define the quality. I will call it as X, and the quality is 0. So I can simply, by having this equation, I can calculate. So I will go to the solve and press on solve. And according to this equation, nu F is equal to 0.00074, which is equal to this value according to this data, to this table data. And then I'm going to calculate the specific volume for this saturated vapor, which is nu G actually. So I will go to here, copy this one, paste, and then change this one to nu G, and then volume, the refrigerant, but this time quality is equal to 1. So we can see this one in the formatted equation also. This is our equation, and Vf1 Vg, and then I can simply solve this one. And as you can see here, this Vg is equal to 0.1104. 1104, roughly the same as this value. Okay, so since this nu that we calculate here is between this nu F and nu G, so the refrigerant we can conclude that is in the saturated mixture region. So I can write this one as a note here. So actually I know this is something like this. Okay, so we can, because we are in the saturated mixture, we can simply calculate the temperature T1 for this refrigerant, which is the saturated temperature. We have this function in the ES. I can go to the function information, still R134A, and then here you can find out the temperature, saturated temperature here. So I can just simply click here and then paste here. I will call this one as T1, correspond to this P1, and then we have here T saturate, and the pressure is 180, which is this one. I will call it as P1. Then I will go to the formatted equation, saturated temperature for this refrigerant in this pressure, and then I will solve this one. So the temperature here is minus 12.73 Celsius. So if I go again to this table, I'm just verifying the ES software data with this reference table. So you see the temperature, saturated temperature for this pressure is minus 12.73, which is equal to this value. So I can go to the equation window again. So here I have determined the temperature of the refrigerant, and then now I'm going to calculate the quality of this refrigerant at this region, saturated liquid vapor mixture. So here also I can go simply to this function information and find out for the quality, which is here. So I will select the quality and then paste the quality here. So for this, I can also call this one as X1, for example, or I can keep it as it is. I can simply use it in the next equation. So I will keep it as X quality for this refrigerant. But here we need to put two input data for this one, but available data. So I can simply use the pressure and the specific volume for this refrigerant. So this is the ES ability, that you can change this input value to other available ones. So I will call it as P equal to P1. And here, as you know, we have this specific volume. So I can call it as V equal to nu that we defined here, nu. So based on this specific volume and also this pressure, we can find the quality of this refrigerant as in the given data. So I can just simply calculate, and then the quality of this refrigerant is 0.1756, which is a unitless quantity actually. Then to determine the specific enthalpy for refrigerant, I can go again to the equation, and then I can use the function for enthalpy and use these two input value. So I will go here simply to the function information. Then I need to find out the enthalpy. So I will go here. Then here I have access to the enthalpy. So I will press enthalpy, paste here. I can call it as H1, for example. And then instead of this TMP, I will use this P1 and also specific heat. Then I can simply use a solve button and then determine the actually H1, which is equal to 71.46. I can simply determine the unit also here. I will go to this H1 here, then select here, right click, and then select the kilojoule per kilogram, paste, and then press OK. If I solve one more time, so this unit also given here. But there is another way you can determine this enthalpy here by determination of the enthalpy of fluid and then this vapor. Then you can use a formula in the thermodynamic and then determine this value. We can calculate and then compare with this value. Okay, so let's get started here. So I will go again to the function information, select the enthalpy here, then I will call it as underscore F. I think it's it should be R134A, and then I can use this one for this fluid region. So I can call it as X01 and the P1. Let me try one time if it will be solved or not. Yes, so HF is 34.97. Then I can do the same for this vapor region. So I will paste here and change this F to G, and then change this actually quality to 1 for the vapor line. So then I can calculate, and then you see this Hg is equal to 242.9. And here also I can determine the units here by going here, then right click, kilojoule per kilogram. You can also copy and paste from the previous one. Solve again. And it is good if you put one equation, solve it, and then see the results, because if you have any mistake, you can find out at that specific time. Otherwise, you need to find out where is the problem in your code. Now I'm going to calculate the H1, but in this time based on the formula, thermodynamic formula. So I will call it as like this, for example, which is equal to, and it's a famous formula in thermodynamic. So if I go here, I have a picture of this one. So the average value for each value, like enthalpy here, is equal to that value, for example, HF, plus the quality multiplied by the YFG. This is the YFG is, in this case, is the for example, Hg minus Hf. So we can use this formula in here. So I will go here and then call this one as HF, H underline F plus X, which is this value, multiplied by H underscore G minus H underscore F, and then this is the HFG actually. So now I can calculate this H1 based on the formula and solve this one. So here, as you can see, this is the first H enthalpy that we calculate from the ES directly, and here we use the formula, and you see the values are exactly the same. I can also give a actually unit to this one, just copy and paste here and then press OK. And so we specify the enthalpy of this refrigerant, and then finally we are going to calculate the volume occupied with the vapor phase. So here I can just simply write this formula. This quality, as you know, is equal to the mass of the vapor, I will call it as M underscore G, divided by the total mass, which is M here. So if I go here, you see this formula, the quality is the actually mass of the vapor divided by the total mass. So if I calculate and solve this problem, so I can simply have this mg 0.79 kilogram. So I can also change this unit, copy here, paste, and then go to here, and then we can define the volume of the vapor phase here. So I will call it as Vg equal to M underscore G multiplied by nu G that we determine here. So this is the specific heat, a specific volume. This is total volume, and this is the mass. So if I go to this formula, you will see this one. So I can simply, based on this equation, I can calculate the Vg. These two are now known data. So I can solve this one, and then this actually volume occupied by the vapor phase is this value 0.08722, and then I can go here and then copy and paste here for this vapor side, and then press OK and solve the equation. So here you see how we can go to the saturated liquid vapor region and determine the properties simply. So this is the procedure we usually do. So I show you how we can calculate and find the actually this question through the table and also through the ES softwares. And you can see the ES software, you can simply access to many data for many different refrigerant. Thanks for your time, and thank you again that you're watching our tutorials. I hope to see you in the next tutorial.